Hello, settle in, get comfortable, and prepare for a journey to the furthest frontiers of our understanding of reality. Imagine looking into a mirror. You raise your right hand, and your reflection dutifully raises its left. Everything is symmetrical, everything is correct. Now imagine that one day your reflection doesn't just mirror your movements, it winks at you when you didn't wink back. Sounds like the opening scene of a horror movie, right? But what if I told you something similar might be happening to the entire universe? What if our reality is a massive cosmic mirror and the reflection no longer matches the original? Today we're going to explore a striking and elegant theory that suggests our universe has a twin, an anti-universe, existing, in a sense, on the other side of the Big Bang. This theory doesn't just sound beautiful, it might hold the keys to the most fundamental questions: why we exist at all, what dark matter is, and what the true nature of time might be. It's a story about grand symmetry, and why its barely noticeable breaking could be the key to everything. To truly grasp the essence of this idea, we need to travel back to the very beginning, to the moment time and space were born. According to the standard cosmological model, 13.8 billion years ago the Big Bang occurred. From a singularity burst forth all the energy and matter that make up everything we see. Physics tells us that in that primordial fire, energy should have created matter and antimatter in absolutely equal quantities. For every particle, like a proton or an electron, there should have been an identical twin antiparticle, an antiproton or a positron. They share the same mass but have the opposite charge. And this is where the first great mystery arises. When a particle meets its antiparticle, they annihilate, disappearing in a flash of pure energy. If they had been equal, all of the matter in the universe should have annihilated itself in the very first moments after the Big Bang, leaving behind nothing but a cooling sea of radiation. But that didn't happen. You exist. I am speaking these words. Galaxies, stars, and planets exist. This means that for some reason, for every billion particle-antiparticle pairs, there was one extra particle of matter. This tiny 1 in a billion imbalance is the reason everything exists. But where did it come from? The standard model of particle physics, for all its successes, cannot provide a clear answer. This is the greatest unsolved problem in cosmology, known as the universe's baryon asymmetry. It is precisely in attempting to solve this that the idea of the cosmic mirror was born. So let's take a deep dive into the problem of this fundamental cosmic imbalance. Picture a set of perfectly calibrated scales. On one side, we place all the matter created in the Big Bang, and on the other, all the corresponding antimatter. Theoretically, those scales should remain in perfect equilibrium. However, the reality we observe tells a dramatically different story. The scale holding matter is clearly tipped. There is virtually zero existing antimatter in the observable universe. Yes, we can produce it momentarily in particle accelerators, and it occasionally appears during extreme astrophysical events, but it simply does not form galaxies, stars, or planets. Our entire visible universe is made exclusively of matter. This isn't just a minor statistical deviation, it is a fundamental defining characteristic of our reality. Back in 1967, the Soviet physicist and dissident Andrei Sakharov formulated three crucial conditions that must have been met in the early universe for such an imbalance to occur. These conditions are, first, processes that violate the conservation of baryon number, meaning that protons and neutrons must be able to convert into other types of particles. Second, the violation of fundamental symmetries known as C and CP symmetry, which we will discuss in more detail. And third, the violation of thermal equilibrium. The trouble is, the physical laws we currently know, even accounting for Sakharov's conditions, cannot explain the observed excess of matter. The predicted imbalance is far too small, many orders of magnitude less than what is actually required. It's like trying to explain the existence of the entire ocean when all you have at your disposal is a single drop of water. Physicists have since proposed numerous exotic theories involving new particles and interactions, yet none have been experimentally confirmed. The core problem remains: why isn't the universe empty? Why are we here? The idea of a mirror universe offers a radically different perspective. Perhaps we are looking for the answer in the wrong place entirely. Perhaps the imbalance never existed at all. To understand how this is even possible, we need to talk about symmetry. In physics, symmetry is more than just an aesthetic concept. It's one of the most powerful guiding principles we have for building theories. Symmetry essentially means that if you perform a certain transformation on a system, the fundamental laws of physics that describe it remain unchanged. Let's focus now on the three key discrete symmetries that are foundational to this discussion. The first is charge symmetry, or C-symmetry. C-symmetry states that if you take any physical system and swap all particles for their corresponding antiparticles, electrons for positrons, protons for antiprotons, and so on, the resulting antimaterial world must obey the exact same physical laws. For instance, an atom of antihydrogen made of an antiproton and a positron should behave exactly like a regular hydrogen atom. Its energy levels, its emission spectrum, everything should be identical. For a very long time, physicists were absolutely convinced that nature strictly adhered to this symmetry. It seemed so incredibly natural and elegant. The universe, they reasoned, shouldn't draw distinctions between positive and negative charge, or between matter and antimatter. It was a deep belief in the fundamental impartiality of the laws of nature. Imagine looking at the world through magical spectacles that instantly flip every charge. C-symmetry posited that the universe seen through those glasses should look and act completely indistinguishably from the one we see normally. But, as is often the case in science, this beautiful, elegant theory eventually ran headlong into a stubborn fact. This fact revealed a flaw, even in this seemingly perfect mechanism. This flaw was the first real hint that the universe's mirror might not be as perfect as we thought. The second fundamental symmetry is parity, or P-symmetry. It deals with spatial inversion, which simply put is the symmetry between left and right. Imagine you are building a complex mechanism, say a watch. P-symmetry suggests that if you were to construct an exact mirror image of that watch, where every left-handed component is replaced by a right-handed one, the mirrored timepiece would function identically, governed by the exact same physical laws. Intuitively, this makes perfect sense. Why should the laws of physics care whether we are talking about a left hand or a right hand? Indeed, the forces of gravity and electromagnetism strictly obey this symmetry. If you look at the solar system reflected in a mirror, the planets would orbit in the opposite direction, but Kepler's and Newton's laws would apply to them just the same. For decades, physicists considered P-symmetry an inviolable truth. However, in 1956, something happened that fundamentally shook the pillars of the physical world. The American physicist of Chinese origin, Qian-Xiong Wu, performed an ingenious experiment studying the beta decay of cobalt-60 nuclei. She cooled the nuclei almost to absolute zero and placed them in a strong magnetic field to orient their spins in a single direction. She then observed the direction in which the resulting electrons were emitted during the decay. If P-symmetry had held true, the electrons should have been emitted with equal probability both along the spin direction and opposite to it, but the result was staggering. The vast majority of electrons were flung out in one strictly defined direction. The world reflected in the mirror did not behave like our own. It turned out that the weak nuclear force responsible for beta decay grossly violates P-symmetry. At a fundamental level, the universe distinguishes between left and right. This was akin to discovering that a screw turned counterclockwise behaved completely differently from one turned clockwise. The mirror of the universe had just sustained its first major crack. The discovery that C-symmetry and P-symmetry were violated came as a profound shock. It felt as though nature itself was capricious and fundamentally asymmetrical. But physicists are determined people. They quickly formed a new hypothesis. What if they combined these two broken symmetries? What if they applied both transformations simultaneously? This combined transformation is called CP symmetry. CP symmetry suggests that if you take any physical process, swap all particles for antiparticles, the C transformation, and simultaneously reflect it in a mirror, the P transformation, the resulting process should obey exactly the same fundamental laws. It was like trying to fix a shattered mirror by gluing the pieces back together. If the standard mirror, P, was broken, and the antimatter mirror, C, was also broken, perhaps the combined reflection, the antimatter mirror, CP, was still perfect? This new combined symmetry looked far more robust. It seemed to restore a crucial balance. For example, if we applied this symmetry to the famous Wu experiment, when observing the mirror reflection of decaying anti-cobalt nuclei, the positrons, anti-electrons, would fly out just as the electrons do in our world. For a time, it seemed that harmony was restored, and CP symmetry was indeed a true, fundamental law of nature. This was critically important because, as we recall, CP violation is one of Sakharov's conditions for explaining the cosmic dominance of matter. If CP symmetry were absolute, the rate of matter creating reactions would exactly equal the rate of antimatter creating reactions, and no cosmic imbalance could ever arise. But then in 1964, physicists James Cronin and Val Fitch, while studying the decay of exotic particles called neutral kaons, discovered a tiny but undeniable violation of this combined symmetry as well. It turned out that even the CP mirror was slightly warped. This discovery earned them the Nobel Prize and delivered a second, even deeper blow to the idea of perfect universal symmetry. Yet simultaneously it provided immense hope, because this violation, slight as it was exactly what was required to explain our very existence. So, C symmetry is broken, P symmetry is broken, and even their combination, CP symmetry, is slightly violated as well. It seems the universe is fundamentally built upon asymmetry and imperfection, but physicists had one last crucial ace up their sleeve. This is the third fundamental symmetry, time reversal symmetry, or T-symmetry. It states that if you record any physical process and play it backward, the reversed process will still obey the laws of physics. On a macroscopic level, this seems incorrect. Thanks to the second law of thermodynamics, entropy always increases. A coffee mug falling off a table and shattering into 1,000 pieces will never spontaneously reassemble itself and jump back onto the table, even if time were reversed. But at the level of fundamental particle interactions, most processes are time reversible. For example, two billiard balls colliding, played in reverse, looks completely realistic. The physical equations describing gravity, electromagnetism, and the strong nuclear force remain unchanged if you replace time et with -t minus t. However, just like with CP symmetry, it turns out that the weak nuclear force also violates T symmetry. Processes involving neutral kaons when played in reverse time happen with a slightly different probability than those in forward time. It appears that at the most fundamental level, time has a preferred direction, its own arrow. Thus, all three discrete symmetries, C, P, and T, are individually violated. The universe is not symmetric when replacing particles with antiparticles. It's not symmetric under mirror reflection, and it's not symmetric under time reversal. It's like finding a statue where the right arm is broken, the left leg is missing, and the statue itself is leaning awkwardly. But what happens if we look at all three transformations combined? And now we reach the pinnacle of the story of symmetries, the monumental, arguably unbreakable CPT theorem. It states that if you apply all three fundamental transformations simultaneously to any physical system, replace particles with antiparticles, C, reflected in a mirror, P, and reverse time, T, the resulting system will be absolutely indistinguishable from the original in terms of the laws of physics. CPT symmetry isn't merely another hypothesis, it's a fundamental theorem proven within the framework of quantum field theory based on very general and reasonable assumptions such as Lorentz invariance, meaning the laws of physics are the same for all observers, and causality. To this day, not a single experimental observation contradicts CPT symmetry. It stands as our last bastion of order in a universe of broken symmetries. It's like taking a crooked object. If you view its reflection in a distorted mirror inside a room where the clocks are running backward, you would behold something perfect. The CPT theorem has profound implications. For instance, mandates that the mass and lifetime of a particle must be precisely equal to the mass and lifetime of its corresponding antiparticle. Any discrepancy in these parameters, no matter how tiny, would lead to the collapse of all modern physics. Experimenters have measured the masses of the proton and antiproton with incredible precision, finding them equal to within 2 parts in a billion. CPT symmetry has passed every single test. This leads the proponents of the mirror universe theory to ask a masterful question. What if this symmetry doesn't just apply to individual processes within the universe, but to the universe as a whole? What if our universe itself is merely one half of a larger system that is, taken entirely, CPT symmetric? This concept, proposed by physicists at Canada's Perimeter Institute, including Neil Turok, completely flips our understanding on its head. According to their hypothesis, the Big Bang wasn't the beginning of everything out of nothing. Instead, it was the moment a pair was born, a universe and an anti-universe. Our universe, filled with matter, expanded forward in time from the Big Bang singularity. Meanwhile, its twin sister, the anti-universe, filled with antimatter, raced away from that exact same point, but backward in time from our perspective. Picture a stone dropped into a calm lake. Ripples spread outward in all directions from the impact point. Now, imagine that in 4-dimensional space-time, the Big Bang is that center point, with our universe spreading out in one temporal direction, and its exact double expanding in the opposite direction of time. This anti-universe is an exact CPT reflection of ours. This means it consists of antimatter, charge, or C conjugation. Its spatial coordinates are mirror images, parity, or P inversion, and for us, its time flows in reverse, time reversal, or T symmetry. From the perspective of a hypothetical observer in that anti-universe, everything looks perfectly normal. To them, their universe is expanding and evolving forward in time, while our universe, which they perceive as being made of antimatter, is moving backward. The concepts of forward and backward in time suddenly become relative. This whole model restores global balance and symmetry. This 2-part system, which one might call a multiverse, is perfectly CPT symmetric and fundamentally flawless. It solves the puzzle of why there is excess matter over antimatter. It doesn't. They are simply separated into these 2 halves. Furthermore, it didn't emerge from nothing. It represents a natural state with 0 total energy and 0 net baryon number. It simply is. Let's take a closer look at how elegantly this hypothesis resolves the problem of baryonic asymmetry. As we recall, the mystery centered on where all the antimatter went, the antimatter that should have been created in equal measure during the Big Bang. The standard approach posits a specific physical process in the early universe that would have created a tiny excess of matter particles over antiparticles. The mirror universe theory tells us you're looking in the wrong place. There was no excess, there was no imbalance. Matter and antimatter were produced in strictly equal quantities. Instead, all the matter ended up in our half of the cosmos, while all the antimatter ended up in the other. It's similar to trying to figure out why the Earth's North Pole only has ice without knowing about the South Pole, which also only has ice. The problem isn't the process of ice formation, it's that you are only seeing half the picture. Crucially, this model avoids the need to introduce new exotic particles or interactions that violate the baryon number, as required by Sakharov's conditions. The structure of space-time itself, the inherent duality of the universe's birth from the Big Bang, provides the necessary separation. This solution possesses an astonishing simplicity and beauty, qualities always highly valued in theoretical physics. Instead of complicating the model of the early universe with auxiliary entities, it proposes a shift in the fundamental paradigm, a change in how we view the Big Bang entirely. The Big Bang ceases to be the absolute beginning of time. Instead, it becomes a point of symmetry, a sort of hilltop from which two twin worlds roll away in opposite directions. Thus, the puzzle that has confounded cosmologists for over half a century might not be a puzzle at all, but simply a consequence of our limited view of the cosmos. We are merely living on one side of the mirror, unaware of what is happening on the other. Let's now discuss what this mirror universe actually looks like. We've established that it is composed entirely of antimatter. That means it must contain anti-stars shining with antiphotons, and anti-galaxies revolving around centers made of antimatter. If we could somehow send a probe there, it would instantly annihilate upon contact with any particle, but the most intriguing features are its spatial and temporal properties. This universe is a p-reflection of our own. That means all chiral, or handedness, properties are inverted. For instance, in our world, all amino acids that form proteins and sustain life are left-handed. In the anti-universe, any life forms, should they exist, would be built from right-handed anti-amino acids. The weak force, which differentiates between left and right in our universe, would operate in a completely mirror fashion there. All neutrinos in our universe are left-handed, and all antineutrinos are right-handed. In the anti-universe, this would be reversed. All antineutrinos would be left-handed and neutrinos right-handed. This inversion holds the key to another great mystery we'll discuss soon, the puzzle of dark matter. But perhaps the most mind-bending property of this universe is its time. Relative to us, time flows backward. What exactly does that imply? Imagine a film of our universe expanding, galaxies fly apart, and entropy increases. If we could watch a film of the anti-universe's lifespan, we would see anti-galaxies converging, and its entropy, from our perspective, would be decreasing. For its inhabitants, however, the reverse is true. Their own entropy is increasing, their time is flowing forward, and our universe appears to be collapsing into a singularity. This raises profound philosophical questions about the nature of time and causality. Is the arrow of time a fundamental, universal property, or is it merely a local phenomenon dependent on which of the two universes you happen to inhabit? This naturally leads to a crucial question. Is all this just a beautiful mathematical game, a purely theoretical construct with no hope of empirical verification? Any robust scientific theory must make testable predictions, and the mirror universe theory delivers on this front. These predictions concern one of the most elusive and mysterious particles in existence, the neutrino. In the standard model of particle physics, we only account for left-handed neutrinos and right-handed antineutrinos. Their mirror counterparts, the right-handed neutrinos and left-handed antineutrinos, are currently missing from the theory, but the CPT symmetric universe model demands their existence. After all, if our universe is indeed a mirror reflection of an anti-universe, every particle must have its symmetrical partner. Consequently, right-handed neutrinos must exist. The theory's proponents suggest that these sterile, or right-handed neutrinos do, in fact, exist. However, unlike their left-handed counterparts, they do not participate in the weak nuclear force, making them incredibly difficult to detect. They only interact with our visible world through gravity. Crucially, the model also predicts the mass of these particles. Calculations suggest this mass must be enormous, around 10 to the 14th power giga-electron volts, making them quadrillions of times heavier than a proton. And this is where the story gets really compelling. These super-heavy, stable, gravitationally interacting particles, predicted solely from universal symmetry considerations, turn out to be the perfect candidate for dark matter. Let's pause for a moment and remind ourselves exactly what dark matter is. It's often considered the second great mystery of modern cosmology, right after baryonic asymmetry. Astronomers noticed that galaxies spin far too fast. The outer stars move at virtually the same speed as the inner ones, almost as if the entire galaxy were a solid, rigid disk. Newtonian physics and the laws of gravity tell us this shouldn't happen. The further a star is from the center, the slower it should orbit. To explain this anomaly, we have to assume that visible matter, the stars, gas, and dust, makes up only a tiny fraction of the galaxy's total mass. Approximately 85% of that mass must be some hidden, invisible substance we call dark matter. It doesn't emit, absorb, or reflect light. We only know of its existence because of its gravitational influence on visible matter. It acts like an invisible cosmic glue holding galaxies and clusters of galaxies together. Without it, they would simply fly apart. For decades now, physicists have been trying unsuccessfully to detect the particles of dark matter. Numerous candidates have been proposed, ranging from lightweight axions to heavy WIMPs, weakly interacting massive particles. Massive underground detectors have been built, attempting to catch the rare collisions between these particles and normal matter. But so far, nothing. Every search has come up empty, and this failure seriously undermines many popular theoretical models. And against this backdrop of failure, the mirror universe hypothesis emerges and claims we know exactly what dark matter is. It's those very right-handed neutrinos, the ones necessary to restore the global symmetry of the cosmos. Their predicted mass and properties fit perfectly to explain all of our astronomical observations. So, how exactly does this model account for dark matter? It posits that a vast quantity of these super-heavy right-handed neutrinos were created at the moment of the Big Bang. Because these particles are extremely massive and stable, the model predicts they cannot decay into other particles. They have persisted to the present day. They participate in no interactions except gravity, which makes them truly dark. They form gigantic gravitational halos, acting like cosmic cocoons inside which visible galaxies coalesce. This picture aligns perfectly with the standard cosmological model known as lambda CDM, where CDM stands for cold dark matter. Cold simply means that the dark matter particles moved slowly in the early universe, allowing them to clump together effectively and form the deep gravitational wells that subsequently drew in ordinary matter. These super-heavy right-handed neutrinos fit the description of cold dark matter, Exactly. What is particularly compelling about this idea is its naturalness. We are not introducing a new particle ad hoc solely to explain dark matter. This particle arises as a natural and unavoidable consequence of requiring the entire multiverse, our universe, plus the anti-universe, to obey CPT, symmetry. Dark matter stops being an isolated puzzle and becomes part of a unified solution, one that also explains the asymmetry between matter and antimatter. Two of cosmology's greatest mysteries are solved with a single, elegant sweep of theoretical thought. This is the hallmark of a very strong and promising theory. It doesn't just patch holes in the standard model, it offers a fundamentally new, deeper, and more symmetrical picture of reality, where the existence of dark matter is as natural as the existence of our own visible universe. Beyond merely explaining dark matter, the mirror universe theory yields other very specific and verifiable predictions. One such prediction relates to the masses of our ordinary left-handed neutrinos, the ones detectable in our experiments. We know neutrinos possess mass, though it is incredibly tiny. This was confirmed by experiments observing neutrino oscillations, the phenomenon where one flavor of neutrino, be it electron, muon, or tau, spontaneously morphs into another while traveling. This transformation is only possible if the particles have mass. Yet the standard model currently predicts that neutrinos should be massless. This represents another significant inconsistency between the model and observed reality. In stark contrast, the CPT symmetric universe model not only mandates that neutrinos must possess mass, but also provides a concrete prediction for the total sum of their masses. This specific mass value stems from a complex quantum mechanical interaction between our light, left-handed neutrinos and their super-heavy right-handed counterparts, which are hypothesized to constitute the dark matter. This interaction, known as the seesaw mechanism, naturally explains why our neutrinos are so incredibly light. The heavier the right-handed partner is, the lighter the left-handed neutrino becomes. The theory predicts the total sum of the three neutrino masses should be approximately 0.12 electron volts. Crucially, this value is within the detection capability of upcoming cosmological surveys and advanced laboratory experiments. Should future measurements confirm this predicted total neutrino mass, it would provide the most powerful indirect evidence yet in support of the entire mirror universe concept. This is a classic case where the reflection holds the key to the original. The minuscule, barely perceptible mass of the lightest particle in our universe could be a direct signature pointing to the existence of its super-heavy twin residing in the mirror world. Another crucial prediction this theory makes concerns the very nature of the neutrino itself. Is a neutrino its own antiparticle? Particles that are their own antiparticles are known as Majorana fermions, named after the Italian physicist Ettore Majorana, who predicted their existence. Conversely, if a particle and its antiparticle are distinct, like an electron and a positron, they are called Dirac fermions. The standard model of particle physics offers no answer to this question for the neutrino. However, the mirror universe model unambiguously predicts that neutrinos must be Majorana particles. This is a direct consequence of the mechanism that generates their mass through interaction with their right-handed partners. So how can we test this? The key lies in a hypothetical process called neutrinoless double beta decay. Some atomic nuclei are known to undergo standard double beta decay, where two neutrons simultaneously convert into two protons, emitting two electrons and two antineutrinos. This process is regularly observed in labs, but if the neutrino is a Majorana particle, a different, much rarer process is theoretically possible. Two neutrons transform into two protons and two electrons with no neutrinos escaping. The antineutrinos emitted during the decay essentially meet and annihilate each other immediately because the particle and antiparticle are fundamentally the same, and thus they never leave the nucleus. Experimenters worldwide are currently hunting for this neutrinoless decay. Its detection would be an event comparable in significance to the discovery of the Higgs boson. It would serve as direct proof that the neutrino is a Majorana particle and therefore provide a powerful piece of evidence supporting the theory that predicts it. The search requires massive, highly sensitive detectors constructed from ultra-pure materials, housed in deep underground labs to shield them from cosmic radiation. If this rare decay is ever confirmed, it will mean we have looked into the mirror and grasped yet another fundamental property of our world, one dictated by its hidden cosmic twin. Our third key prediction concerns the very earliest moments of the universe, focusing specifically on inflation and gravitational waves. The standard inflationary model posits that in the first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. This inflation effectively smoothed out the universe, making it as homogeneous and flat as we observe it today. Crucially, it also generated the primordial density fluctuations that eventually grew into galaxies. One of the hallmark predictions of inflationary theory is the generation of primordial gravitational waves, ripples in the very fabric of space-time. These relic gravitational waves should have left a distinct imprint on the polarization of the cosmic microwave background, which is often called the echo of the Big Bang. Astronomers are actively searching for this specific signal using instruments like the BICEP/Keck array at the South Pole. However, the mirror universe model offers a radically different perspective on the cosmos's earliest history. In this model, there is no need for a standard inflationary field or inflaton. Instead, the key properties of the early universe, including its flatness and homogeneity, are explained by the underlying CPT symmetric structure itself. This model makes a hard, concrete prediction: primordial gravitational waves of inflationary origin should not exist. More accurately, their amplitude must be below the threshold of detection for the foreseeable future. This gives us a clear criterion for falsification. If experiments in the coming years successfully detect primordial gravitational waves, it would strike a critical blow to the mirror universe theory. Conversely, if the search remains unsuccessful and we continue to set tighter and tighter upper limits on the amplitude of these waves, it would strongly reinforce the position of CPT symmetric cosmology. This is a perfect example of how science works. A theory makes a bold, risky prediction, and its ultimate fate rests on the results of future observation. We are living in a unique time where the answer to what happened in the very first second of the universe's existence may well be revealed within our lifetime. Let's recap the predictions of this concept to truly appreciate its elegance and explanatory power. First, it solves the problem of baryon asymmetry without introducing new interactions, simply by postulating the existence of a CPT symmetric twin of our universe. Second, it naturally generates a dark matter candidate, a super-heavy right-handed or sterile neutrino, which is a necessary element for the restoration of symmetry. Third, it predicts a specific value for the total mass of standard neutrinos, which future experiments can verify. Fourth, it posits that neutrinos are Majorana particles, a claim we can test by searching for neutrinoless double beta decay. And fifth, it predicts the absence of observable primordial gravitational waves resulting from cosmic inflation. No other theory to date boasts such a comprehensive scope of fundamental problems and such a powerful set of concrete, testable predictions. This theory doesn't just solve one isolated issue, it offers a unified, coherent framework for understanding the biggest mysteries in particle physics and cosmology. It links the subatomic realm of neutrinos to the macroscopic universe of galaxies and dark matter. It connects our present to the earliest moments of the Big Bang. And all of this rests on one simple yet profound concept, the principle of CPT symmetry applied to the universe as a whole. Of course, this is not yet a proven theory. It may turn out to be wrong, but its internal consistency, its mathematical beauty, and its immense predictive power make it one of the most exciting areas in modern theoretical physics. It forces us to look at the world and our place within it in a whole new light. Now let's take a moment to reflect on the deeper philosophical and worldview implications of this idea. If this theory holds true, it means our universe is not all there is. It is merely one half of a larger, fundamentally symmetric structure. This effectively demotes our cosmos from its pedestal of uniqueness to the status of just one of two components forming a whole. This concept echoes ancient myths and philosophical teachings about dualism, the unity and struggle of opposites, yin and yang, chaos and order. But here, this dualism takes on a concrete physical form, matter and antimatter, time flowing forward and time flowing backward. Our existence, composed of matter, turns out to be not a privilege, but merely a random outcome, a coin flip between two possibilities. In the anti-universe, an anti-physicist might be asking why his world is made of antimatter instead of matter. The very concept of time becomes fundamentally more complex. If there exists a twin universe where time, from our perspective, flows in reverse, it completely undermines our intuitive perception of time as a universal, one-way river. Perhaps the arrow of time is merely a localized phenomenon determined by the thermodynamics within each twin universe. At a more fundamental level, the level of the entire CPT symmetric multiverse, there may be no preferred direction of time at all. The Big Bang ceases to be an absolute beginning and is instead redefined as a point of bifurcation, a point of symmetry. This resolves the uncomfortable question of what happened before the Big Bang. The answer may be that there was nothing, because the question itself is fundamentally ill-posed. The Big Bang is not an event in time, it is the event that generated time itself, simultaneously launching it in two opposite directions. Perhaps the most compelling argument for this theory is its sheer minimalism. Just think about the number of additional entities other theories have had to invent just to patch up the holes in the standard model. To explain cosmic inflation, we need the inflaton, a new scalar field burdened with highly specific properties. To account for dark matter, we must postulate WIMPs or axions, entirely new classes of particles that remain completely unobserved. To solve the problem of baryonic asymmetry, physicists often require novel interactions that violate fundamental conservation laws. The mirror universe theory demands none of these complex additions. Instead, it builds upon the existing components of the standard model, adding only one necessary ingredient, the right-handed neutrino. Crucially, this particle is not introduced arbitrarily. It is required to restore fundamental symmetry and acts as the natural counterpart to the left-handed neutrino we already know exists. This entire concept strictly adheres to the principle known as Occam's razor. Do not multiply entities beyond necessity. It offers the most economical and elegant solution to several major cosmological puzzles simultaneously. Rather than just sketching in new details onto the existing canvas, this theory asks us to step back, view the picture from a new angle, and realize that the whole structure is far simpler and more symmetric than previously imagined. History teaches us that in science, the most profound and correct theories are often the most beautiful and the simplest. Copernicus's model streamlined Ptolemy's complex system of epicycles. Einstein's theory of relativity eliminated the need for the clumsy concept of the luminiferous ether. Perhaps just like those prior breakthroughs, the idea of a CPT symmetric multiverse will prove to be the simple, beautiful key that finally unlocks the next great door in our understanding of the cosmos. Let's now address the potential objections and weak spots of this theory. No scientific theory is ever perfect, and this one certainly raises its own share of questions. One of the main sticking points concerns the moment of the Big Bang itself. In this model, that initial point remains a singularity, a spot of infinite density and temperature where the laws of physics, as we currently understand them, simply break down. While the theory elegantly describes what happens after this point, projecting forward and backward in time, it fails to describe the point itself. For a complete understanding, we still require a unifying theory of quantum gravity that can successfully bridge general relativity and quantum mechanics. Another open question is the exact mechanism that caused the two universes to separate and evolve precisely the way they have. Why did all the matter coalesce here, while all the antimatter ended up there? The theory postulates this separation as a consequence of CPT symmetry, but the detailed dynamical mechanism driving this split still needs to be fully worked out. Furthermore, while the theory offers specific, testable predictions, verifying them pushes the very limits of our current technological capabilities. The search for neutrinoless double beta decay is an immensely complex experiment that could take many more years to resolve. Likewise, accurately measuring the total sum of neutrino masses is an incredibly demanding task. Moreover, even if we fail to detect primordial gravitational waves, this absence could still be accounted for by specific conventional inflationary models. In short, no single test is absolutely definitive on its own. Only the convergence of results from several independent experiments will ultimately be able to confirm or refute this elegant hypothesis. But that, ultimately, is the essence of the scientific process, the long, meticulous work required to rigorously test bold and ambitious ideas. Let's compare this theory with its main competitor in explaining the early universe, the inflationary paradigm. Inflation, as we've discussed, posits an incredibly rapid, exponential expansion immediately following the Big Bang. It brilliantly solves several major cosmological puzzles: the horizon problem, why widely separated regions of the universe, unable to exchange information, still have the same temperature; the flatness problem, why the geometry of our universe is so close to being Euclidean; and the monopole problem, why we don't observe the exotic, heavy particles that should have been created in abundance. However, inflation has its own significant difficulties. Firstly, the nature of the inflaton, the hypothetical field that drove this expansion, remains completely unknown. Secondly, most inflationary models lead to what is called eternal inflation, which spawns an infinite collection of bubble universes with varying properties, a concept that renders the theory virtually untestable. The mirror universe theory offers alternative solutions to some of these same issues. For instance, the horizon problem can be resolved by assuming that before the Big Bounce, the moment replacing the Big Bang, there was a contracting phase during which the entire universe was causally connected. Furthermore, flatness and homogeneity are natural consequences of the CPT symmetric construction itself. Crucially, it avoids the problem of eternal inflation entirely and offers a far more constrained and predictive cosmological scenario. Ultimately, we are dealing with two distinct philosophical approaches. The inflationary paradigm attempts to explain the observed properties of our world by introducing new entities and mechanisms into its deep past. The mirror universe paradigm seeks to explain those same properties based on a fundamental principle of symmetry that links our world to its invisible counterpart. Which of these two frameworks will ultimately prove correct remains for the future to decide. Let's return to our original metaphor, the mirror. We previously noted that the reflection no longer precisely matches the object. But now we understand that this mismatch is the essence of the matter. It's not a flaw, it's the single, most important piece of information we can gather. Imagine looking into a perfect mirror. You learn nothing new about yourself beyond what you already know. Now imagine that the mirror is slightly distorted. The nature of those distortions allows you to deduce a great deal about the properties of the mirror itself. In our analogy, the tiny, subtle asymmetries of our world are precisely these distortions, telling us about the properties of the global CPT symmetric multiverse. The violation of CP symmetry in kaon decays, which allowed matter to triumph over antimatter in our half of the universe, is not an error of nature, but a necessary condition for our existence, perfectly compensated by an inverse process in the anti-universe. The minute mass of the neutrino is not a random constant, but a direct reflection of the existence of their super-heavy partners, which form the bulk of dark matter. The chirality of life, the fact that all our amino acids are left-handed, is not a coincidence but a consequence of the p-symmetry violation by the weak interaction, which takes the opposite sign in the anti-universe. It follows then that the most fundamental and mysterious properties of our world are the very seams and fissures on the surface of the cosmic mirror, through which we can reconstruct a complete, symmetric, and far more grandiose picture of reality. We are that non-matching reflection, and it is precisely within this discrepancy that the ultimate solution lies. This theory also compels us to reconsider the concept of the multiverse. Over the past few decades, this idea has become immensely popular in physics and cosmology. However, it's typically linked to frameworks like string theory or eternal inflation, which postulate the existence of a practically infinite number of universes, each governed by different physical laws and constants. This so-called landscape of universes is incredibly difficult to verify, leading many critics to accuse it of straying from true science and entering the realm of metaphysics. The multiverse proposed by the CPT symmetric model is completely different. It is not an endless ensemble of random worlds, but a strictly defined, minimalist structure consisting of just two components, our universe and its exact CPT symmetric counterpart. It is not a multiverse, but rather a biverse. Crucially, unlike the complex inflationary landscape, this model yields concrete, testable predictions about the properties of our own world. While we cannot directly observe or communicate with this anti-universe, we can study its indirect manifestations right here in our labs by examining the properties of neutrinos, searching for neutrinoless double beta decay, and measuring the parameters of the cosmic microwave background. We are, in essence, studying the properties of the entire biverse as a whole. This represents a far more scientific and productive approach to the multiverse concept. It successfully pulls the idea back from the realm of philosophical speculation and grounds it in verifiable physics. This may be the first concrete step toward realizing that our world is not unique, yet it is not lost among an infinite spray of random possibilities. Instead, it is part of an elegant, ordered, and dualistic structure. Let's visualize the possible history of such a bi-universe. At time t equals 0, the Big Bang occurs, or perhaps the Big Bounce, from a previous phase of contraction. From this central point, moving into positive time, our universe begins to expand and cool. The processes we know well unfold here. Particles and antiparticles are born, but with a slight prevalence of the former, caused by CP symmetry violation. Antimatter annihilates, leaving behind the baryonic matter from which stars and galaxies are formed. The universe continues its expansion driven by dark energy. Simultaneously, from that same point t equals 0, the anti-universe begins its evolution in the direction of negative time. For us, its time flows backward. It also expands relative to its own temporal flow, but it consists of antimatter. It, too, possesses a slight excess of antibaryons over baryons. Anti-galaxies and anti-stars form within it. Its entropy increases in its own direction of time. From the viewpoint of a god, or a hypothetical observer situated outside of time, the entire picture appears perfectly symmetrical. It's like an hourglass where sand pours simultaneously from the center in both directions. The net total of sand, matter, and antimatter remains constant, equaling 0. The total entropy of the system can also remain constant, as the increase in one half is compensated by the increase in the other. This scenario possesses a profound aesthetic appeal and completeness, qualities so sorely lacking in the standard cosmological model with its unaccounted-for initial conditions and broken symmetries. And what about dark energy? This is the third great puzzle of cosmology. Observations of distant supernovae in the late 90s revealed that, contrary to expectations, the expansion of our universe was not slowing down due to gravity. Instead, it was accelerating. To explain this phenomenon, the concept of dark energy was introduced. It's a mysterious substance with negative pressure distributed uniformly throughout space, acting effectively as an anti-gravity force, pushing galaxies apart. Dark energy accounts for roughly 70% of the total energy density in the cosmos. The standard model offers no explanation for its nature or magnitude. Theoretical calculations of its density derived from quantum physics yield a value that is 120 orders of magnitude larger than what is observed. This represents the greatest discrepancy between theory and experiment in the history of science. Can the mirror universe theory shed light on this mystery too? Directly, no. In its current form, it makes no specific predictions about the nature of dark energy. However, it may be compatible with certain intriguing ideas. For instance, if we consider the entire bi-universe as a single system, we could hypothesize that its total cosmological constant, the value that describes dark energy, is 0, which would be the most natural outcome from a symmetry perspective. The small positive value we currently observe could then be a mere fluctuation effect, or the result of interactions between the two universes. These are currently just speculations, but they demonstrate that this new paradigm might open fresh avenues for solving this third great problem. If dark energy can successfully be integrated into this framework, we would achieve what physicists call the theory of everything, a unified description of all fundamental forces and particles in the cosmos. Let's return now to the right-handed neutrinos, which, within this specific model, serve as the dark matter particles. Why do we call them sterile? Because they do not participate in 3 of the 4 fundamental forces, the strong, the weak, and the electromagnetic. They only feel gravity. This makes them almost impossible to detect directly. They pass right through us, through the Earth, and even the Sun, leaving absolutely no trace. However, they aren't completely sterile. As we mentioned earlier, they interact very feebly with the standard left-handed neutrinos via the seesaw mechanism. While this interaction is extremely weak, it can lead to one fascinating effect. The super-heavy right-handed neutrinos that make up dark matter might decay, albeit very, very slowly. One possible decay channel involves them breaking down into a standard neutrino and a photon, or alternatively, an electron and a positron. Because their mass is enormous, the resulting energy of the decay products would also be extremely high. If we could capture these high-energy photons or neutrinos coming from all directions in space particularly from the center of our galaxy, where dark matter density peaks, it would constitute direct evidence of dark matter decay. Astrophysical observatories such as the Fermi Gamma Ray Space Telescope or the Ice Cube Neutrino Observatory in Antarctica are specifically searching for these signals right now. So far, no conclusive evidence of dark matter decay has been found, but the search continues vigorously. If such a signal is detected, and if the energy of the decay products matches the predictions of the mirror universe model, it would be a true triumph for this theory, perhaps even more compelling than any laboratory experiment could provide. A natural question immediately springs to mind. If the anti-universe is indeed moving backward in time, doesn't that fundamentally violate the principle of causality? Could we potentially receive information about our future originating from the anti-universe? The short answer is no. The two universes are not causally linked. They intersected at only one single point, the moment of the Big Bang. After that, their trajectories diverged completely. There are no bridges or wormholes connecting them. Information simply cannot cross the barrier created by the Big Bang. Furthermore, the very concept of moving backward in time is relative. To an observer within the anti-universe, their time is flowing forward, and it's our time that appears to be running backward. Their causality functions perfectly within their own direction of time. Events in their past influence their future. None of the classic grandfather paradoxes arise. The true connection between the two worlds is far more subtle. It exists not at the level of direct signal exchange, but rather through the shared laws and fundamental constants established during their co-birth. Think of it like two gears in a mechanism spinning in opposite directions. While they don't exchange information directly, their movement is synchronized and dictated by the overarching design. The properties of neutrinos in our universe know about the existence of their counterparts in the anti-universe, not because they received a signal, but because they are part of a unified quantum mechanical system described by a single equation. This is a very subtle and profound point, which fundamentally separates this theory from naive representations of time travel. It's fascinating to note that the idea of a universe moving backward through time isn't new. Back in the 1940s, the renowned physicist Richard Feynman proposed an interpretation where an antiparticle is simply a regular particle traveling backward through time. For instance, a positron could be seen as an electron whose world line on the space-time diagram points from the future back to the past. While this concept was primarily a mathematical trick designed to simplify calculations in quantum electrodynamics, it has always captivated the imagination. The theory of the mirror universe essentially takes this Feynman idea and applies it not just to individual particles, but to the cosmos as a whole. It elevates the concept from a mere mathematical formalism to the status of physical reality. Our universe is made up of particles moving forward in time, while the anti-universe is composed of those same particles moving backward in time, which is precisely what we perceive as antiparticles. This concept also echoes John Wheeler's whimsical one-particle hypothesis. Wheeler playfully suggested that every electron in the universe is actually the same single electron, traveling infinitely forward and backward through time. Its continuous intersections with our temporal plane are simply what we observe as a multitude of distinct particles. Of course, the mirror universe theory isn't quite so radical, but it certainly inherits this spirit, the enduring quest to find deep connections and symmetries hidden beneath the apparent diversity and complexity of the physical world. Let's imagine we live in a world where this theory has already been proven. Future experiments have confirmed the Majorana nature of neutrinos, measured the sum of their masses, and found the result perfectly aligned with predictions. Astronomers haven't found primordial gravitational waves, but they may have detected a signal from dark matter decay. How would our worldview fundamentally change. First, we would obtain a practically complete and self-contained description of fundamental physics. The standard model would be expanded and augmented, and its three main issues, matter asymmetry, dark matter, and the mass of the neutrino, would be solved within a single, unified concept. This would be an achievement comparable to the creation of the standard model itself in the 1970s. Secondly, our understanding of the cosmos would become far stranger, yet simultaneously more ordered. We would know that our world is just one of two halves of reality, that there exists a mirror world made of antimatter where time flows backward. This knowledge most likely wouldn't have any practical application in everyday life, but it would fundamentally reshape our philosophical perception of existence. We would realize we are part of a grand, perfectly symmetrical structure. Perhaps it would even influence our art, culture, and religion, much like the theories of Copernicus or Darwin's theory of evolution once did. The knowledge that the universe has a flip side would compel us to look anew at everything, from the origin of life to the ultimate fate of the cosmos. What, then, is the ultimate fate of such a bi-universe? Our universe, as we currently understand it, is undergoing accelerated expansion, likely headed toward heat death, a state of maximum entropy. This is the point where all stars have burned out, black holes have evaporated, leaving only a cold, dark, and empty space populated by scattered, rare particles. And what about the anti-universe? For its inhabitants, it faces the same destiny within their own time frame. But for us, external observers, its evolution appears as a contraction toward the Big Bang singularity, with entropy decreasing. This paints a fascinating picture. Perhaps the entire bi-universe, taken as a whole, is stationary or cyclical. It's possible that the moment of the Big Bang is not only a point of birth for us, but also a point of death for the anti-universe, and vice versa. Some cyclic cosmological models suggest that an expansion phase is followed by a contraction phase, culminating in a new Big Bang. In the context of our theory, perhaps our universe and the anti-universe represent these two phases of the same eternal cycle. Our universe is the cosmos's exhale, and the anti-universe is its inhale. They don't follow each other sequentially, but exist simultaneously, like two sides of the same coin, ensuring the eternal existence and rebirth of reality. This, of course, moves beyond the bounds of rigorous science and into the realm of metaphysical speculation. But it is precisely such ideas that are born at the intersection of great theories, constantly expanding the boundaries of our knowledge. Ultimately, the mirror universe theory represents one of the most beautiful, audacious, and promising ideas in modern fundamental science. It offers solutions not just to one, but to several of the deepest mysteries in physics and cosmology, relying on one of the most foundational concepts, the principle of symmetry. The theory claims that the imbalance and asymmetry we observe in our world are merely an illusion generated by our local viewpoint. When we step back and look at the whole picture, we find a perfect CPT symmetric order, where our universe and its anti-counterpart, which moves backward through time, are two perfectly balanced halves of a unified whole. This theory makes several specific testable predictions concerning the properties of neutrinos, dark matter, and the cosmic microwave background radiation. Its ultimate fate will be determined by experiments and observations over the next few decades. Regardless of whether it proves correct in the end, it has already played a crucial role by forcing us to fundamentally reconsider the very nature of time, matter, and symmetry. It has shown that sometimes, to solve the most complex puzzle, the answer is not to introduce new components, but simply to look at the existing picture in a mirror. And perhaps the truth is hidden precisely there, in that distorted, mismatched reflection. So, we've completed our journey right into the heart of the universe's greatest mysteries, and we've seen how one single, elegant idea can illuminate them all. The universe, it turns out, is a mirror, and the most stunning discovery is this. Its imperfection, its asymmetry, the slight mismatch between reality and its reflection. This isn't a defect. It is the key to understanding everything. It is this very mismatch that allowed us to exist. It is this asymmetry that points toward the hidden nature of dark matter. And it is this very factor that defines the minuscule mass of the most elusive particle of all, the neutrino, the hypothesis of an anti-universe, our CPT symmetric double existing on the other side of the Big Bang transforms apparent chaos into perfect order. It suggests that our world is only half the story, one side of a coin. On the reverse side, there is an identical world made of antimatter where time flows backward. This theory is still waiting for confirmation or refutation, but it has already fundamentally changed how we view reality, demonstrating just how profound, strange, and beautiful the structure of our cosmos truly is. Thank you for spending this time with me contemplating the mechanisms of our universe. I hope this lecture has given you plenty of food for thought and perhaps a peaceful night's sleep. Don't forget to subscribe to the channel, like this video, and hit that notification bell so you don't miss our next journey to the frontiers of the known. And now for the big question I have for you. What do you think lies on the other side of the cosmic mirror? Does our anti-copy truly exist there, living life in reverse? Share your thoughts in the comments below. Good night.